So now let's talk about the extension of PRSA to derive LDA. And to motivate that, we need to talk about some deficiency of PRSA. First, it's not really a generative model because we can't compute the probability of a new document. You can see why, and that's because the pi's are needed to generate the document, but the pi's are tied to the documents that we have in the training data. So we can't compute the pi's for a future document. And there is some heuristic workaround though. And secondly, it has many parameters, and I've asked you to compute how many parameters exactly there are in PRSA, and you will see there are many parameters. So that means the model is very complex, and that also means there are many local maxima, and it's prone to overfitting, and that means it's very hard to also find a good local maximum, and that really represents a global maximum. And in terms of explaining future data, we might find that it would overfit the training data because of the complexity of the model. The model is so flexible to fit precisely what the training data looks like. And then it doesn't allow us to generalize the model for using on other data. This, however, is not necessarily a problem for text mining because here we are often only interested in fitting the training documents that we have. We are not always interested in modeling future data. But in other cases, or if we care about the generality, we would worry about this overfitting. So LDA is proposed to improve that, and it's basically to make PRSA a generative model by imposing a Dirichlet prior on the model parameters. Dirichlet is just a special distribution that we can use to specify prior. So in this sense, LDA is just a Bayesian version of PRSA, and the parameters are now much more regularized. You will see there are many fewer parameters. And it can achieve the same goal as PRSA for text mining. It means it can compute the topic coverage and topic word distributions as in PRSA. However, there's no free lunch. While the parameters for PRSA are much fewer, there are fewer parameters. And in order to compute the topic coverage and word distributions, we again face the problem of inference of these variables because they are not the parameters of the model. So the inference part again faces the local maxima problem. So essentially they are doing something very similar. But theoretically, LDA is a more elegant way of looking at the topic modeling problem. So let's see how we can generalize PRSA to LDA or extend the PRSA to have LDA. Now, a full treatment of LDA is beyond the scope of this course, and we just don't have time to go in depth in talking about that. But here I just want to give you a brief idea about what's the extension and what it enables. Right. So this is a picture of LDA. Now I remove the background model just for simplicity. Now, in this model, all these parameters are free to change, and we do not impose any prior. So these word distributions are now represented as theta I vectors. So these are word distributions, right? So here. And the other set of parameters are pi's, and we represent it as a vector also. And this is for convenience to introduce LDA. And we have one vector for each document. And in this case, in theta, we have one vector for each topic. Now, the difference between LDA and PRSA is that in LDA, we're going to not allow them to freely change. Instead, we're going to force them to be drawn from another distribution. So more specifically, they will be drawn from two Dirichlet distributions respectively. A Dirichlet distribution is a distribution over vectors. So it gives us a probability for a particular choice of a vector. Take, for example, pi's, right? So this Dirichlet distribution tells us which vector of pi's is more likely. And this distribution itself is controlled by another vector of parameters alphas. Depending on the alphas, we can characterize the distribution in different ways. It would force certain choices of pi's to be more likely than others. For example, you might favor a choice of a relatively uniform distribution over all the topics, or you might favor generating skewed coverage of topics, and this is controlled by alpha. And similarly here, the topic word distributions are drawn from another Dirichlet distribution with beta parameters. And note that here alpha has k parameters corresponding to our inference on the k values of pi's for a document, whereas here beta has m values corresponding to controlling the m words in our vocabulary. Now, once we impose these priors, then the generation process will be different. And we will start with drawing pi's from this Dirichlet distribution. And this pi will tell us these probabilities, right? And then we're going to use the pi to further choose which topic to use. And this is, of course, very similar to the PRSA model. And similarly here, we're not going to have these distributions free. Instead, we're going to draw one from the Dirichlet distribution. And then from this, then we're going to further sample a word. And the rest is very similar to PRSA. The likelihood function now is more complicated for LDA, but there's a close connection between the likelihood function of LDA and PRSA. So I'm going to illustrate the difference here. So in the top, you see PRSA likelihood function that you have already seen before. It's copied from previous slide, only that I dropped the background for simplicity. So in the LDA formulas, you see very similar things. First, you see the first equation is essentially the same. And this is the probability of generating a word from multiple word distributions. And this formula is a sum of all the possibilities of generating the word. Inside the sum is a product of the probability of choosing a topic multiplied by the probability of observing the word from that topic. So this is a very important formula, as I have stressed multiple times. And this is actually the core assumption in all the topic models. And you might see other topic models that are extensions of LDA or PRSA, and they all rely on this. So it's very important to understand this. And this gives us the probability of getting a word from a mixture model. Now next, in the probability of a document, we see there is a PRSA component in the LDA formula. But the LDA formula would add some integral here. And that's to explain, to account for the fact that the pi's are not fixed. So they are drawn from a Dirichlet distribution. And that's shown here. That's why we have to take the integral to consider all the possible pi's that we could possibly draw from this Dirichlet distribution. And similarly, in the likelihood for the whole collection, we also see further components added, another integral here. Right? So basically, in the LDA, we just added these integrals to account for the uncertainties. And we added, of course, the Dirichlet distributions to govern the choice of these parameters, pi's and thetas. So this is the likelihood function for LDA. Now let's talk about the parameter estimation and inferences. Now the parameters can be now estimated using exactly the same approach, maximum likelihood estimate for LDA. Now you might think about how many parameters are there in LDA versus PRSA. You will see there are fewer parameters in LDA because in this case the only parameters are alphas and betas. So we can use the maximum likelihood estimate to compute that. Of course, it's more complicated because the form of likelihood function is more complicated. But what's also important is to notice that now these parameters that we are interested in, namely the topics and the coverage, are no longer parameters in LDA. In this case, we have to use Bayesian inference or posterior inference to compute them based on the parameters alpha and beta. Unfortunately, this computation is intractable, so we generally have to resort to approximate inference. And there are many methods available for that, and I'm sure you will see them when you use different toolkits for LDA, or you read papers about these different extensions of LDA. Now, here we, of course, can't give in-depth introduction to that, but just know that they are computed based on Bayesian inference by using the parameters alphas and betas. But algorithmatically, actually, in the end, in some algorithms at least, it's very similar to PRSA, and especially when we use algorithm called collapsed Gibbs sampling, then the algorithm looks very similar to the EM algorithm. So in the end, they're doing something very similar. So to summarize our discussion of probabilistic topic models, and these models provide a general principled way of mining and analyzing topics in text with many applications. The best basic task setup is to take text data as input, and we're going to output k topics. Each topic is characterized by a word distribution, and we're going to also output proportions of these topics covered in each document. And PRSA is the basic topic model, and in fact the most basic topic model. And this is also often adequate for most applications. That's why we spend a lot of time to explain PRSA in detail. Now, LDA improves over PRSA by imposing priors. This has led to theoretically more appealing models. However, in practice, LDA and PRSA tend to give similar performance. So in practice, PRSA and LDA would work equally well for most tasks. Now, here are some suggested readings if you want to know more about the topic. First is a nice review of probabilistic topic models. The second paper has a discussion about how to automatically label a topic model. Now, I've shown you some distributions and they intuitively suggest the topic, but what exactly is the topic? Can we use phrases to label the topic to make it more easy to understand? And this paper is about the techniques for doing that. The third one is an empirical comparison of LDA and PRSA for various tasks. The conclusion is that they tend to perform similarly.